Hello, everyone. My name is lcar Torres Quijano, and I will be talking about the enhanced SNR full width at maximum and Strehl ratio improvements through mid-infrared drift scanning, utilizing the Canary Cam instrument at the GTC. So quick overview, I will be making a short introduction here on Shopknot and Driftscan. We will go through the methodology we utilized to compare both methods. Then we would look at results, some applications, and of course, the conclusions. So the Shopknot technique is utilizing in mid-infrared since there are multiple sources that can contribute to a background. This includes the Earth atmosphere, telescope mirrors, the instrument entrance window. And to remove this background, the Shopknot technique is commonly used by oscillating a secondary mirror at a particular frequency to subtract that background. The secondary mirror is moved to an on-source and off-source position where a set of images are acquired. And then the on-source and off-source images are differenced to obtain a signal, which is known as a shot cycle. However, chopping does introduce detrimental effects to the data, which includes the degradation of the PSF, the reduction of on-source collection time, the creation of a radiative offset, which is addressed by nodding the telescope. Optical aberrations can also be induced in the shot beam, and the off-source beam can contain other sources. When you combine all of these effects together, the observing efficiency for the GTC instrument is approximately 32%. The technique also faces the issue of it being impossible to utilize for future 30-meter class telescopes due to the secondary mirror being too large to shop. So how can we address these issues? One of these ways would be to utilize the Driftscan technique. It can be performed in one of two following ways, where the telescope is held at a single position with respect to the mount, or the telescope being driven at a user-defined speed across the sky field. If the latter, then a pattern can be traced, as seen in the figure on the right, due to short exposure times, and subsequent frames can be differenced from a previous frame to remove the background. So as mentioned, the technique allows us to have short exposure times that'll enable us to sequence future frames from earlier frames to subtract the sky background. And you can co-add those different frames during the data reduction phase to produce a final image. Drift scanning allows us to keep that secondary mirror fixed, which raises the observing efficiency to approximately 100%. And optical aberrations are not present since you're not doing any shopping. For the Driftscan data, we recorded the Driftscan in a rectangular immersion across the array, as seen in the previous figure. This rectangular shape was chosen for two reasons: to characterize the performance for the drift directions in the X and Y throughout the detector channels, and to minimize the synchronization requirements between telescope drift and instrument integration. The Driftscan speed was approximately 3 pixels per second in our data set. Quick note on drift speed: if the drift speed is too low, then the background subtraction will be inferior. And if the drift speed is too fast, then the observation target could be elongated. So how did we go about reducing our drift scan data? Well, we had our raw frames, right? We can take that raw frame and we produced a median filter of 5 spatially separated frames, so that we can remove the source from it. And that medium frame can be used as a proxy for the background. We can take those subtracted frames and remove the source that is there. And then we can move into the frequency space by using a Fourier transform to identify if there's any array readout noise. By identifying that noise, we can isolate it, and we can then transform that noise back into the image space, subtract that as well from our data, and then we can extract the source from that clean frame and combine the data. So how does this look like with our images themselves? So we have that raw frame here, and the source is here, barely visible in that area. And we can make that medium frame to remove it. And then we can then subtract both to have the source and that first frame. We can remove that source there to move into that frequency space. And then we can see those, what we call trend lines, being the array readout noise for our particular case. We moved into the image space, and then we can finally have a clean frame by subtracting that as well. And then we can produce a final image by repeating this process for every individual frame and extracting the source and co-adding at the end. So for Shopknot, we actually did 4 different reductions. However, we're going to be talking about 2 in this particular case. We did that standard reduction from the GTC and Canary Cam. However, seeing that we identified that array readout noise, we saw that we can also perform that here for the Shopknot. So we have those raw frames and the shop difference beams. However, here we remove both sources there because of that chopping. And then we can do that process again by going to frequency space and identifying the noise source. Once you subtract that noise, we can have our final image by extracting the source. And it looks fairly similar to that flowchart, except of course we don't have that median frame. But in essence, we go into frequency space after removing those sources. We have those trend lines, and then we can clean up the noise and produce a final image. So the first thing that we notice here, Driftscan image on the left, the Shopknot on the right, we have a increased signal, as we can see here on the left, those sharper yellow pixels, and of course the fidelity of the image is higher. And as we can see, there are 3 airy rings that are clearly visible, with a 4th being potentially visible there. And if we move here into a 3-dimensional representation of the signal, we can see that significantly increased peak here on the Driftscan on the left. So how did we go about doing the data analysis? Well, we recorded the signal to noise ratio with fixed aperture photometry and optical aperture photometry. We recorded this noise far from the object. And we also recorded the full width at maximum, the Strehl ratio. Here we can see the Strehl ratio with Driftscan was 54% when compared to a 35% with the Shopknot and the standard reduction. And the delta SNR here will be the ratio between Driftscan and Shopknot SNR. And we can see that for the standard reduction that GTC and Canary Cam provides, we had a 254% increase in the optimal aperture photometry here. So what applications can we do? Well, for Tau-Mizunsuku, for example, Driftscan could be tested at a higher wavelength coverage since it goes from 2 to 38 microns. The wider FOV would let us test for drift scanning with multiple stars in that FOV. And Tau being located at a height of 5,600 meters in Atacama, Chile, the sky conditions would be especially attractive for these observations due to reduced seeing effects. So the key takeaways, drift scanning can remove many of the detrimental effects seen with the Shopknot technique. Drift scanning can offer an improved signal to noise ratio due to the larger observing efficiency. The medium frame technique, as well as the array readout noise identification, allow for better noise sampling and removal. And of course, in our case for GTC and Canary Cam, we saw an improved Strehl ratio from 35% to 54%. These are some of the acknowledgements, the ERDF, the support of the Department of Physics and Astronomy at UTSA, John and Sharon Kuzowicz for their support in my graduate studies, and Dr. Fuller and Mason Leist for their support during the whole process. And of course, that would be the end of my talk. And if you have any questions, feel free to ask.
Thank you very much for a very nice talk. It seems it's very powerful, impressive technique. And we do have questions. And I think the first one is from Enrique. No one raised a hand here, I guess. Okay, from Enrique. Do you have to read it out yourself, or I would be happy to do it, but.
Yeah, I can do it.
Yep. Cool.
Awesome. Yeah, thank you. Hey, Amilcar, very exciting observation techniques and results for point sources in 10 microns observation. So even though this is very exciting, so I'm wondering how would an object with extended emission will be recovered? So let's say that you're observing the galactic center with emission everywhere and with larger extension than the array. So I'm wondering how this technique will handle extended emission, and if you have tried map making algorithm typically used in submillimeter or far infrared observations?
Okay, yeah, so in our case, as we saw, we did a standard star. So I'm gonna transfer this question, if that's okay, to Dr. Packham, if that's okay, for extended edition.
Absolutely, great question, Enrique. So I think what it depends on is having enough of the array kind of blank that we can sample that noise. So it wouldn't work if the array was, say, more than 50% occupied by a source. So in your example of the galactic center, I think, no, I wouldn't see a way to easily apply this technique. You could modify the technique to apply it, but in the way that we're doing it thus far, it wouldn't work. Does that address your question, Enrique?
Yeah, I think that map making algorithm, like the ones used in balloons of submillimeter or cosmic background, those are the way to do it. And with scanning in a different way, that would be the way to do this kind of recovery.
As you know, Enrique, with you're hanging out on GrantaCan a lot. I think most of the objects that we looked at were pretty compact, and so I think for some of our stuff, this could work out pretty well, as it's much less than half the array.